Today I'd like to talk about cavity resonators. And it's a pretty interesting topic. And you have come across resonators before as an electrical engineer. And the place where you have come across a resonator is an LC tank circuit, for instance. When you have an LC tank circuit, there would be certain frequencies at which I guess you have learned this from your undergraduate day. If the frequency is 1 over the square root of omega square root of L times C, then the resonator can resonate. The characteristic of a resonator is that it does not require an external driving source. For instance, if you think of this as a circuit thing, you don't need an external driving source to get the current going back and forth. There will be current going back and forth between the capacitor and the inductor due to the exchange of magnetic energy stored and electric energy stored, but you don't need an external driving source to make that happen. The energy just goes back and forth by itself. Okay, what are resonators good for? You probably have seen that in your undergraduate day. If you have a voltage source, okay, and if you want to transfer this to a load, let me call this a Z load. You can transfer the energy from the voltage to the load this way, but if you want to preferentially transfer only a certain frequency, you can put an LC tank circuit in parallel. And when the frequency is hitting the resonance frequency of the LC tank circuit, this becomes an open circuit. And the transfer of energy is perfect. However, at other frequencies, then the LC tank circuit acts like a shunt impedance. Okay, you know that when an LC tank circuit is at resonance, its impedance is infinite. Away from resonance, its impedance is not infinite, so it can be acting like a short circuit or a shunt impedance to actually not allow all the energy to be transferred to the load. Okay, so this is a very rudimentary kind of a filter. So you can use LC tank circuit as a filter. And how do we make a resonator out of all the things that we have known now? We can start with the simplest resonator we can make from a transmission line. Just take this figure over here. If I were to have, this is not a source now, this is impedance of the source, and this is the impedance of the load. And imagine a wave bouncing back and forth between the two ends. And imagine that these loads are lossless so that they don't absorb energy. Then the wave can bounce back and forth forever, giving rise to a resonant condition, very much like the energy in the resonator, the LC tank circuit going back and forth between the inductor and the capacitor. But this is the energy bouncing back and forth inside a transmission line waveguide. Okay, so how can we use a transmission line model to study this problem? We can use the transmission line model by using the transverse resonance condition. Just a reminder, we now know that many things can be modeled as a transmission line. We have seen that when you have, say, a rectangular waveguide, you can actually model a rectangular waveguide as a transmission line as well as sections of transmission line. Even if you have a circular waveguide, you can model it as a section of transmission line by exploiting mathematical homomorphism. Okay, so you can have cylindrical waveguides of any cross section or even microstrip lines. If you have a microstrip line, such as this one, say if you make a microstrip line on top of a substrate, let me draw the substrate this way. And then usually you have this thing sitting on a substrate, and then there's a ground plane below. Let's assume that this is the ground plane. Okay, a ground plane. And you can also think of a microstrip line with a quasi TEM mode as a transmission line. And you can think of that can be becoming a resonator when you terminate a transmission line with two impedances. Well, what is the theory behind this? The theory behind this is that for resonance to occur, you need resonance condition. And we can easily use the transverse resonance condition to derive the resonance condition, very much like we use that to derive the wave guidance condition. We said that a solution may exist in this transmission line if after the wave has bounced back and forth from the two ends, and then after it has traversed the length of the transmission line with this phase factor. Okay, so this transverse resonance condition is very much like what you have learned before, where gamma L and gamma S are the reflection coefficients at these two ends. This end we will have gamma L, this end we will have gamma S. Those are the two reflection coefficients, and then the wave is assuming to propagate back and forth with a phase velocity related to beta z. Okay, so you can intuitively write down as the resonance condition for this wave to sustain itself without being canceled out. So this wave will bounce back and forth and interfere constructively within this section of the waveguide, and this solution can exist without an external driving source. And when something can exist without an external driving source, like the case of an LC10 circuit, we say that that is the resonance solution. Okay, let's see what the possibilities are. Well, if we have say a short or an open, gamma L is either plus or minus 1. Gamma S is equal to plus or minus 1 for short and open loads. Okay, those you can find very easily. If the transmission line is terminated with other kinds of loads, you know how to find those reflection coefficients too. But then solving this equation will be too difficult. So we just do the simplest case, where we have terminated the transmission line with either short or open. Depending on the situation, we can have two cases. One is equal to e to the minus j 2 beta zd is one case. And the other case is when the left-hand side becomes minus 1. There are a few combinations. There are 4 combinations for the product of gamma S times gamma L. So you can have but only 2 equations that comes out. These are the 2 possibilities. Okay, so for the left-hand equation, you can easily solve it. It should be that 2 beta zd is equal to n pi, no, 2n pi. Okay, when you require that 2 beta zd is 2n pi, or beta zd is n pi, where n is an integer, then the resonance condition will be satisfied. However, for the other one, you will have to have 2 beta ZD to be n pi, where n is odd. So if you pick 2 beta ZD to be n pi where n is odd, then this equation would always be satisfied. So this means that beta ZD is n pi over 2, where n is odd. Okay. So you can have different kinds of solutions, and you probably know what the solutions are. You can go back and fill yourself in using a transmission line model. So the solution will look something like that. And for the left-hand side one, which is the one shown here, okay, this one, the wave actually make a full half wavelength from one end of the transmission line to the other end. So if I were to draw this transmission line, the left-hand solution will have solutions where it starts with 0 and it becomes something like that. That's when beta ZD is equal to n pi. And the next one would be something like this. Okay, and then next one would be something like this. But always ending with a 0 at it, 2 ends, and these are the cases where beta ZD equals n pi. Okay, n is an integer. However, the other case is if you have a transmission line, you don't know what the loads are. The loads will be maybe one side is short circuit, the other side is open circuit. Then you will have this being -1 on the left-hand side, because if one of this is a short circuit, the other one is an open circuit, you get a minus sign in total. And this equation is the equation that you have finally. And so you have the case where beta ZD is n pi over 2 and odd. And you can actually figure what the voltage pattern should be like. This is actually the current. Okay, I'm actually plotting the current here. Current should be 0 at the 2 ends, is what you have. And similarly, if you plot the current here, the first mode would be something like current being 0 and then being the maximum near the short circuit. And then the next mode would be something like this, being the maximum near the short circuit. I didn't draw it well, but you know what I mean, okay? And then you can draw the next mode. Okay, always with this ending with an open circuit. No, not ending with the open circuit, ending with the maximum current. The current will be max here, will be 0 here. And if you were to plot the current distribution on this transmission line, you will have all these different modes. This is n is equal to 1, n is equal to 3, and n is equal to 5. Okay, so you can find these resonant modes quite easily. Okay, and that actually we have done before. For instance, we did study this transmission line quite exhaustively. That is when we have a transmission line with a short and an open on the both ends, then you can actually plot the voltage as a function of Z. The voltage should be 0, and then will be maximum at where the thing is open. Then the current would behave the other way around. The current would be the maximum on the left side because it's a short circuit, and then it goes to 0 on the right-hand side because it's an open circuit. So you can make resonators quite easily using transmission lines or waveguides, even if the waveguides can be mapped to a transmission line. Are there any questions so far as to how we can make resonators out of transmission line? So the idea is that if you have a transmission line like a coax, this is the case of a coax. Okay, one way you can make a resonator is to short it at the other end with a metal short, and then you just leave this other side open. Okay. However, if you were to make such a transmission line resonator, this is the coax resonator. Okay, if you were to make a transmission line resonator in this manner, the short is very much like a short, like the figure here, as shown in this transmission line model. However, the right-hand side, if you were to look at the electromagnetic field on the right-hand side, because of this being open circuited, there will be charges accumulating at the end of the cable, and there will be negative charges at the other end. So there will be fringing field that goes like that, okay, from the outer conductor to the inner conductor. And that depends on the phase of the wave, of course. And this fringing field store electric energy, and that has to be modeled with a capacitance called a fringing field capacitor. Okay, and this stores electric field energy. And so this should be the correct model for this transmission line with an open circuit on one end and a closed circuit at the other end. You probably learned from your take-home exam that solving this problem is not trivial. When this is an open circuit, it's trivial. Well, if you were to put in a capacitor here, you will have some transcendental equations to solve. Okay, so one way to solve transcendental equation is to use graphical methods, but I'll leave it for you to play around with if you're interested in finding the resonant frequency of this transmission line. But when this is an open circuit, finding the solution is trivial. Okay.